So remember that in order to calculate a t value, we have to divide by the unbiased estimate of the standard error, which is where the samples come into play. Okay. So all that to say that as part of this process for determining significance of our research, we would calculate our t-value, which we're going to call our calculated t. Remember that for this example, we calculated a t of 2.35. Now we're coming to table C. We're going to take our degrees of freedom and our alpha level, and we're going to see how those two pieces of information help us navigate table C. When looking at table C, you're going to notice that this is called critical values of t. So when I incorporated that language critical t into the slide, that's because I'm drawing it from this table. In order to navigate this, we're going to use this first column identified as degrees of freedom. And we're also going to use this fourth column here identified as 0.05. Each of these columns underneath this bar that says level of significance, those relate to different alpha levels. So this is saying that we can look at alpha levels for 0.20, 0.10, 0.05, 0.02, 0.01, and 0.001. For our class, we're focused on either 0.05 or 0.01. For this problem specifically, we're only focused on 0.05. So we know that whatever critical t value we're going to take from this table, it's going to come from this column underneath 0.05. The point that we have to now wonder is, okay, well, where do we stop? How do we know which of these numbers is the most appropriate one to pull? And that's where our degrees of freedom comes into play. So looking in this first column underneath degrees of freedom, you're going to see all these numbers. And each of these numbers represent different degrees of freedom. If you track down these numbers, what you're going to see is that they work from 1 all the way to 30 by individual whole numbers. So you see every single number from 1 to 30 represented. After 30, however, notice that there's a jump from 30 to 40. So we skip 10. From 40 to 60, we skipped 20. From 60 to 120, we skipped another 60. The reason that as we move further and further up this degrees of freedom, that is because of the central limit theorem that says that the larger our sample is, the more likely it is going to, and you know, the more samples we can take, the more likely we actually are witnessing a normal distribution. So beyond 30, 40, 60, 120, the differences between these critical t values would be so small that it'd be really splitting hairs. And so there's no actual value in demonstrating to you what the difference between 30 and 31 is, or between 40 and 50, or between 60 and 100. So notice then that our degrees of freedom for this problem, 39, is not reflected here in this column, which is okay. I know some of you might be thinking, well, then I'm just going to round and then, you know, whatever number I get closest to. Unfortunately, that's not that way that we actually use these. We would want to err more on the side of being a little bit more conservative with how we're thinking about the differences between these values. And so for any number that appears between the increments, you actually want to go to the lowest, closest degrees of freedom. So even though 39 is numerically close to 40, we're not going to go to 40. We're going to kind of fall back on degrees of freedom of 30. That'd be the same even if the difference between 40 and 60, if we calculated degrees of freedom of 59, yes, it's closer to 60, but we're going to default to using degrees of freedom of 40. Okay. Remember, we are using degrees of freedom, so we've learned that we're going to use degrees of freedom of 30 for this. And then we have our alpha level of 0.05. And what we're effectively trying to do is point out where those two values intersect. So our column of 0.05 is here. It intersects with the degrees of freedom of 30 at this critical t value of 2.042. If I were asking you to report the critical t value, you could either report 2.042 or 2.04. I'm not concerned with the difference between there. Okay. So with that said, let's go ahead and get back to our presentation. All right, so back here at our presentation, we've pulled all the information. We learned that our critical t value for this problem is going to be 2.04 or 2.042. Our responsibility then is The same as our responsibility when we were talking about comparing z-scores, right? I showed you this normal curve, and I said, okay, well, the critical region that we determined, if it falls at 1.96, remember, hopefully this rings a bell for you all, negative 1.96 here. That's because we, as the researchers, decided to use an alpha level of 0.05. But remember that this original illustration that we were introduced to is using z-scores, and we can't use z-scores. We're now using t-scores. So what this means then is that instead of our boundaries falling at a z-score, our boundaries are falling at the critical t-score that we just pulled from the table C. So if we have a critical t of 2.04, that means that 2.04 is our critical region boundary on either side, 2.04. Table C, just like table A, does not show you negative values. And so we are going to compare our calculated t-value to the critical t-value. If the mean is in the middle, everything to the right is positive, everything to the left is negative. We calculated a positive t-value, so we know we're working on the right side of this, this distribution, t-distribution. We know that our boundary starts at 2.04, and when we compare that to our critical value, our calculated value, 2.35, it's going to exist somewhere out here. Somewhere, right? And remember, if it exists in this area, then it is significant. Okay? So we have determined by our analysis that the difference between our West Side residents, the average numbers of their community service when compared to the population average, there is a significant difference between those two numbers. There's not just any difference, it is significant. I want to point out here that I included this last bullet point here that t equals 2.35. Our calculated t is further from 0 than t equals 2.04. Now that's how I want to show you and hopefully help you get comfortable with thinking about comparing these two values. The reason I gave a little asterisk here is because I want to point out that the critical t value is effectively expected to be understood as an absolute value. If you remember learning about absolute values, you may recall that an absolute value doesn't actually have a positive or a negative symbol attached to it. It's just the number by itself. So that's the kind of comparison you want to make. And so I kind of associate that with being further from 0, because even if this were a negative 2.35, then we would still identify negative 2.35 as falling within this critical region. So it still remains a significant finding, but I just wanted to include that just so that you all have an understanding of why it is that we're making the comparison the way that we are. Remember that if it falls in the critical region, that means it is significant. And when the results of a research project determine significance, that's because we are rejecting the null hypothesis. We got to the end of our analysis, we determined their significance, we are rejecting the null hypothesis, which is to say that there is a significant difference between these two groups, right? So I also shared with you at the end of the hypothesis testing presentation that we're going to learn about reporting results, and that how you report results is specific to the kind of test that you're conducting. So this next slide is just that. It is an example of reporting results based on this research that we've just completed about West Side residents. I'm going to read out this paragraph that I've included here just as it is, and then I'm going to come back and highlight some things that are really important. So we would start this off by saying a one-sample t-test was conducted to determine if community engagement levels among West Side neighborhood residents, M equals 6.8, which is our mean hours, SD, standard deviation, equals 4.3, differed from the national average of 5.2 hours per month. Results indicated that West Side residents spent significantly more time on community service activities than the national average. And then there's this information here, T parentheses 39 equals 2.35 with a P of 0.05. I'll explain that all in just a moment. It's highlighted down here, but I'll give you more information. This finding suggests that Westside residents demonstrate higher community engagement, volunteering an average of 1.6 more hours per month than the typical, the typical US adult. Future research may explore the neighborhood-specific social and cultural factors contributing to this enhanced civic participation. All right, so this paragraph here is written according to APA standards. And my expectation is that when I'm asking you all to report results based on your analyses, that you are completing your reports as it according to APA formatting standards. So the way that I've constructed this, that's, I don't want to say copy and paste, right? Because not every single research project that not every analysis that you run is going to be focused on West Side neighborhood residents. But if you think of this as kind of a formula, I want your reported results to follow this formula. Okay. Notice here that this first sentence is giving a little recap of what we did, right? We are conducting a one sample t-test to determine community engagement levels among West Side neighborhood residents. We included this information in parentheses. Notice that this M is capitalized and it is italicized. That is the way you are always going to include this. Capitalized, I'm just going to write it as cap plus italicized. Always, always, always. Always, okay? Capital M, italicized, there's a space here, equals space 6.8 hours, comma, space SD, standard deviation, also capitalized and italicized. Okay? Always equals 4.3. This is based off this information that we drew from our sample of West Side residents. It's also indicating that it differed from the national average of 5.2. Remember that in this case, I would be giving you the information, and so you would drop that in here. What are you comparing it against? Results indicated that West Side residents spent significantly more time. How do we know that it's significantly more time? The reason that we know is that our sample was 6.8 hours on average, and our national survey data said 5.2 hours on average. So this piece about more time isn't just, something we're pulling out of nowhere. It's because we calculated a difference. If this were less than 5.2, let's say our West Side residents only did community service for 3 hours when compared to a national average of 5.2, we would identify that it was maybe significantly less time if we, got to the end and still rejected the null hypothesis. So this more time isn't just arbitrary, it's according to whatever the results of your test are. On community service activities, then the national average. And then we have this formula thing here. This formula thing is always structured this way, and I've included it down here to get you to really think about this like a formula. So what's written in black as part of this, that is always, always, always the case. Don't modify it, don't change it. T, open parentheses, and then close parentheses, and equal sign, those things are expected to be there. What is going to change based on your test is going to be this piece about the degrees of freedom. We determined that degrees of freedom for our specific sample ended up being 39. We calculated that. So we incorporate our degrees of freedom into this number. This calculated T ratio is the one that we calculated. Remember that we did the math in order to determine that our calculated T was 2.35. We plugged that in right here. This comma is always supposed to be there. Space, I forgot to let you all know there should be a space here, space here. There's a space between the comma and P, space between P and this greater than symbol, and then 0.05. This one gets a little bit trickier. When we are doing our analyses by hand, in the context of kind of all doing this together, I give you an alpha level, right? 0.05 or 0.01. If we were doing, these calculations by hand, and I gave you the information to just do this by hand, you are going to write whatever alpha level I give you. However, when we are working in SPSS, SPSS actually calculates a specific probability value for the likelihood of you getting your calculated T ratio. When we get into SPSS, we're going to be presented with exact probabilities. I'm going to write SPSS here. At that point, when I'm asking you to report results based on